Saxon Advanced Mathematics, Lesson 5. This is part 2. We're just wrapping up. I got my charger now. And we should be fine. I was down to 9%. Hopefully we're good now. This is the geometry portion of Lesson 5, which is beastly. In this lesson, John's playing with a problem that often showed up on SAT type tests. And it's not a trick problem, but it is a confusing problem. And I just want to walk you through it so you can get the hang of it. They're not hard once you understand what John's trying to get you to understand about the diagrams. The scale factor between two rectangles is 4. Scale factor equals 4. I don't normally work with the scale factors, but they're easy to figure out. What is the ratio of the areas? That's the question. All right, let's figure this out. We've got two rectangles. Here's one that's smaller, and the other one is 4 times bigger. I'm not going to draw that much bigger. Just pretend. Okay? So if this one this is the width, and this is the length, right? In the big one, this is the width, and this is the length. It's 4 times bigger. We said the scale factor is 4. So that means this dimension is 4 times, and this dimension is 4 times, right? So if we call this rectangle 1 and this rectangle 2, the area of the first rectangle is length times width, right? Or LW. The area of the second triangle is 4L times 4W, or 16 LW. So I wrote that one again. So the ratio of the areas is 16 to 1, right? Because this is 1 and this is 16. So even though the scale factor is 4, the ratio varies by a square of the scale factor because we had to multiply those. That's kind of weird, isn't it? Kind of bends your head a little bit. Let's try it with circles. This is a long lesson, isn't it? The radius of one circle is R. Draw the pictures, you guys. It always helps. And the radius of a second circle, it's actually smaller. I'm just going to draw them roughly the same size. This is 3/5 R. So technically this one is smaller, but I don't want to draw anything smaller than that. What is the ratio of the first circle to the area of the second circle? So this is 1, just like we did here. We're going to name them 1 and 2. This one is going to be pi r squared, right? Area of 1. The area of the second one is going to be pi 9/25 r. I'm just looking at how John presented this. We're on the right track. Okay, so squared. Okay, so the ratio is, we can say that is 1, right? Pi r squared, we can put a 1 in front of everything. So the ratio is 1/9/25, right? This is pi r squared. This is pi r squared. That part stays the same. But just the number that we've created is 1 to 9/25. And then to simplify this as a complex fraction, we would multiply this, top and bottom. This is the reciprocal, so this equals 1. It explodes, it goes away. So the ratio of the area of circle 1 to the area of circle 2 is 25/9. Which freaks out my brain a little bit, but how do you compare that? I don't even know what that means. 16:1 makes sense, but this confuses me to find out what that means. But the main thing I want you to see is just set up pictures, use your formulas, work it through, create the relationship, and simplify. All right? Play with this a few times and see if it makes any sense to you. Let me know if you are just bewildered. Diagonals of rectangular solids. Are you ready for this to be our last topic? I think that would be good. D, diagonals. You know how everybody has this with their name. There are certain words in the English language that sound somewhat like your name, and when you hear people speak them, it catches your attention in a different way. Diagonals was always the one for me because it sounded like my name. And whenever I would hear the teacher say diagonals, I would have a moment of panic because I thought she was going to ask me a question that I didn't know. And so whenever I use that word, I always remember that weird little adrenaline jolt I would get. Example 510. Oh, good, we have a picture. Find the length of the diagonal that connects corners in a picture that I'll draw for you in a minute in the rectangular solid chunk. Okay, these are so fun, you guys. I love the ones where we get to draw three-dimensional objects. Take the time to draw the picture because it will help you understand the problem. Three-dimensional thingy. It's not perfect, and that just makes me sad, but pretend. Okay, then we can imagine these back right? The three-dimensionality of it. That's really sloppy. I'm sorry. I want it to be better. Okay, so we have on the front A, B, C, D. Those are the front four corners. And then the back four corners are E, F. F is a hot mess, isn't it? G is over here, and H is up there. F is the one that just died. That's why I put the F over where the corner is so that you can't see how messy it is. We're looking for the diagonal that goes from B to H. I want to do it in a different color, just so that it stands out a little bit. We're going like this. That's what we're trying to find, is the diagonal of that. Find the length of the diagonal that connects corners B to H in the rectangular solid. Now, here is the drama, you guys. We're not given any numbers. We're just gonna do it with letters. Ay, ay, ay. So, we have two steps. The first thing that we're gonna do is we're gonna find the length of BG. Okay, we're gonna find the length of this first. And then, let's look at that first. So, BG, we're gonna look at this rectangle, basically the bottom of the box. So let's look at that. It's got B on the front corner, F in the back, C here, and G there. We want that line. Okay, I'm going to draw this in. Oops. I'm going to draw this in solid because it's important. We'll come back to that later. So the first step is we're getting kind of the shadow of that line on the bottom. Okay, there's going to be two steps to this, but the first step is to find this one. And that's line BG, right? Because our line is above that, but it's at this angle. Now, this is BG right here, right? So we need to use Pythagorean theorem to solve this. John also tells us this is X and this is Y, the lengths of those sides. So this is X and this is Y. So Pythagorean theorem tells us that A squared plus B squared equals c squared. These are always the legs. This is always the hypotenuse. That's a really sloppy exponent. Sorry. Okay? This is our hypotenuse. So, oh, the other thing we can do is we can rewrite this as, say, c equals the square root of a squared plus b squared. And we don't have to worry about a negative value for that because in geometry, we can't have negative lengths. So we can eliminate that. So if x and y are our legs and BG is our hypotenuse, the one we want, then we can write this. Make sense? Okay, so now we know that this orange line is that dimension long. Now what we want to do is we want to, I just want to make sure I'm doing this in the right order. BG and HG, okay? Now we want to imagine a right triangle that goes from there to there to there. Does that make sense? The triangle looks like this. This is along the floor. This is the orange. If you imagine that box is like a room you could go into, it helps me. The orange is on the line. We can walk along there, and then up ahead, coming from this corner of the floor and going up to the ceiling, is that line. This is the one we're trying to figure out. This one we just figured out is square root of x squared plus y squared, right? That's this. So now we do the very same thing. We use Pythagorean again. I don't know what to call this step. I'm thinking about it. All right. So this time, the height of the box yeah, John told us this in the original picture too, that the height is z. Okay, so these are the lengths of the sides. So now we know that this height is also z. So, again, we're going to use Pythagorean. Let me flip. Okay. I want to set it up here, you guys, so you can see what I'm doing. Then I'll take it over to clean it up a little bit. So, if this is one leg and this is the other leg, then we can use this formula to plug it in again. We'll have the square root of this squared plus z squared. And because this little square root and that squaring cancel each other out, our final answer is x squared plus y squared plus z squared, which is pretty cool if you think about it. Okay? So the hardest part of this problem, we basically use Pythagorean theorem twice. The hardest part is to imagine what you're doing. So just remember, we're standing inside this room. We want this angle that goes up over our heads. We find the shadow of it on the floor first, and then we imagine that slice as a triangle. Okay? So this is our second triangle. Trying to help you just see that's this one. Right? And then this is the floor that we're standing on. All right? This is also a lot harder because we're doing it all in letters instead of numbers. And that's confusing. And John's going to make us do it one more time and then we're done. Ready? Example 5.11. Random markers floating around. All right, find the length of, here we go. It's really fun just drawing these pictures. I enjoy it so much. Okay, it's like this. Kind of, that's a little wobbly, but you know. Okay, and then we're gonna go. All right, there's our box. Let's put some letters on it. This is A. This is B. This is C. Sometimes it helps to put dots there. Uppercase letters usually mean the angles. Lowercase letters often mean the sides. I tend to circle the sides just so I can see what's going on. Okay, we're supposed to find the length of the diagonal in AC. Okay, so it's going from the floor up to the ceiling. That's what we want to find. And remember, the two-step is to find the shadow on the floor first. So we're going to find from C to B first. So I'm going to redraw the floor of the room just as a rectangle. This is C, this is B. This is the orange shadow that's on the floor. I need to know the legs of this. 3 is along here. And then 2 is the length of this side, right? Because it's that one, so it's also that one. So BC equals the square root of 4 squared plus 3 squared. Or, I'm sorry, 2 squared. I squared it in my head, right? Okay. So BC equals, this is 2 squared. That is a mess. So that's 4 plus 9. So this is square root of 13. Okay, so that's square root of 13. Now we need to imagine that triangle. So it's going to be like this. We know that this is the line on the floor. And this is now the line that's going up. We know that the length of this is square root of 13 because we just figured it out, right? Right there. And we know that this height, is it M? I just want to double check. Yeah, it's M. By the way, John tells us not to use the formula that we just worked out in the other problem, which I'm like, fine, John, be that way. Right, so this is M. So it's right there. So this, which is AC, equals, and I'm using the shorthand version of Pythagorean. We just can algebraically rearrange it to look like that. And it's useful for just jumping into the calculation, right? AC is my hypotenuse. It's equal to the square root of 13 squared, right? Because it's this squared plus M squared. Those two cancel, so AC equals square root of 13 plus M squared. That's the right answer. Okay? Once again, the hardest part is just visualizing what's going on. But we're trying to find the diagonal and we look at the shadow on the floor first. Well, that was a fun little warm-up, wasn't it, for your brain? That's lesson 5. It was a lot, 2 parts, geometry and algebra. Buckle in, you guys. We still have a few crazy lessons, but we're getting there. Okay, thank you. See you next time.